Hey folks, we're on to chapter 4 now. We're going to look at the next topic, which actually builds on the previous one. We've previously been talking about polynomial functions, and if I think we saw it was clear that these things are true. If you add two polynomials, you'll just get another polynomial, and if you multiply two polynomials, you'll get another polynomial. But division, they don't play so well with division. If you divide one polynomial by another, things get weird, and that's what chapter 4 is about, that particular weirdness. So let's take a look at the book. The very first thing in this the text for chapter 4 is this definition of what it means to be a rational function. I guess the word rational normally means something like, thinks things through carefully, makes logical decisions. But in this case, it really just comes from the word ratio. We're talking about functions that are the ratio of two polynomials. So, and this is fairly standard use of the letters. We use r of x for the rational function, p of x for the numerator, and q of x for the denominator. So if I just say p, I'm usually talking about the numerator. Likewise, q would be just the denominator. All right, so it starts off with a few examples of what are rational functions. Not all of them look like they're just simply fractions involving polynomials. The first one does, though. 2x minus 1 is a polynomial. In fact, this is a ratio of two linear polynomials, so it's a fairly simple type of rational function. But number 2 doesn't quite look that way. Now, I guess the way we should think of it is, it's not that it has to be handed to us in the form of p of x over q of x, but rather we could put it in that form if we wanted to. So could we make this one in number 2 look like a p over a q? Yeah, you would just have to put them over a common denominator and do the subtraction. So yes, that could be done. 3 has two different fractions subtracted, but you see that they do have the same denominator, so that's sweet. The things can be subtracted directly without having to find a common denominator, and the difference of this polynomial's numerator minus this other one, I can't make it highlight. Still doesn't want to highlight. I keep getting that dictionary thing popping up. Sorry. Anyway, the 2x squared minus 1 minus the 3x minus 2, well, that reduces to a single polynomial. So, yeah, polynomial over polynomial. It's all looking good. This last one, oh my. Well, just remember that when you're dividing one number times another, it's the same thing to multiply by the reciprocal of that number. So if I multiplied by the reciprocal, oh, weird, flipping the second one upside down would mean x squared minus 1 in the numerator, and that would cancel with the x squared minus 1 in the denominator. So there's actually a simplified version of that thing. But now we got to talk about the issue of domains. In fact, that's what these examples are really about, finding the domains of these things. See, if any of the computations that you would need to do to calculate a value of the polynomial involves dividing by 0, that's a spot that's not in the domain. So, well, let's look through them one at a time. Number 1, the bottom of that thing is 0 if x is negative 1. So the domain consists of everything besides negative 1. Let me see, I want to get do some drawing about that one. I think. So, right, our function, let's call it r of x to stay with the letter convention. Oh no, they called it f of x, so I'm going to live with that. F of x is 2x minus 1 over x plus 1. And this is undefined when x is negative 1. But other than that, it's good, right? You can stick any value you want into x other than that minus 1, which is going to make it have division by 0. So our domain for that guy is everything from minus infinity up to negative 1, not including that point, union with everything to the right of minus 1. So minus 1 off to plus infinity. Boom. Number 2, I sort of said how to do this, so let's actually do it now. The function given in that problem was, they called it g of x. It was 2 minus 3 over x plus 1. Now I said you have to put these things over a common denominator and then subtract, but that common denominator won't affect the domain computation. I mean, we could go to the trouble of writing this as one polynomial divided by another. I guess I'll go ahead and do it since I said I would. 2 times x plus 1 over x plus 1. That's replacing the 2 with a fraction that's got the right denominator. Minus 3 over x plus 1. And that is going to simplify like this. The bottom is x plus 1 on both of them. And the top, when we subtract, will be 2x plus 2 and then minus 3. So just 2x minus 1. So there you go. We can do the job of writing it as a fraction of polynomials, but I just want to point out that we didn't need to do that to figure out the domain. Here's the only thing in the computation of g of x that can go wrong: the possibility of dividing by 0 when x is negative 1. So, it's got the same domain as the other guy, doesn't it? See, this thing is undefined also at x equals minus 1, which makes the domain there also be minus infinity up to negative 1, not inclusive, and then from minus 1 off to plus infinity on the other side. Groovy. Same issue is going to happen in number 3. I guess I'll go ahead and do the computation for you. It had a difference of 2 rational functions. So we had 2x squared minus 1 over x squared minus 1 minus 3x minus 2 over x squared minus 1. Well, you can see in that form that the bottoms are the same on both sides. So yeah, these things can be combined in just one step. We don't even have to find the common denominator. We'll have x squared minus 1 down below, and the one quadratic term will be 2x squared. There's no x in that first guy, so minus 3x is the only thing with coefficient that's a coefficient times x. And then we'll have minus 1 and then plus 2, so a total of plus 1. But like before, you only have to figure out where things would go south in the computation. Where would this thing be undefined? And that comes down to noticing where's the bottom 0. It's undefined when, well, watch out for this. When x squared minus 1 is equal to 0. A lot of people will just find the one place, but there's actually 2, because both x is plus 1 and x is minus 1 will give you 0 here. And that is best seen, I think, if you notice that this is a difference of squares, so it factors. So that's x minus 1 times x plus 1 equals 0. And yeah, that's going to be 0 when either term is 0. So once it'll be 0 when x is 1. The other factor tells you it's 0 when x is minus 1. What does that do for us in terms of domain? Well, it's just got 2 breakpoints in it, essentially. We go from minus infinity up to minus 1, and then from minus 1 to plus 1. All of these are round parentheses because those points are intended to not be part of the domain. And then from 1 to plus infinity is the last bit. Okay, so I think I'll leave the fourth one there. You know, the solutions to these things are actually in the text, so you can follow through with those on your own. Number 4 is not that crazy. I do want to, you know what, I got to say something about number 4, because the best way to think about that is we'll flip this guy over, and then we'll cancel something from top and bottom. And if you do that and just look at what remains, it's not so bad. It's only got division by 0 in one location after that cancellation has happened. It would be at x is, what, 2/3, I think. Well, but you see, we have to go back to the originals thing and see when was that going to have a division by 0 error, a moment where it was undefined. And that's not just when x is 2/3, but also when x is plus or minus 1, because you see you have a x squared minus 1 in the denominator of part of what you need to do to calculate the thing. So watch out that you want to watch for the before you simplified form of things when you're calculating domains. All right, there's some features of the graphs of these rational functions that are pretty important. So I figure we ought to look at some graphs, which means I'm going to pull up a Desmos. Here we go. So I want to make a few examples for you. How about R? Why is this not doing what I told it to do? Oh, oh, I'm sorry. Trying to type in a thing that doesn't accept typing. R of x is going to be about x to the second plus 1. That's nice. But now we want to take that thing and divide it by something like x minus 2. Oh, funny looking graph. In fact, I know we're not seeing all of this graph because of, well, because I already know about vertical asymptotes. There we go. If I move it a little bit, you see it. You can always zoom out to try to find it. So why did I know I was going to see something else? There's a line right here when x is equal to 2, where that function would not be defined, right? When x is equal to 2, the bottom is 0. If I plot the line x is equal to 2, actually let's mess with the style of that, because normally when we're doing sorry, I'm trying to change the style of it and I turned it off instead. There we go. When we're doing these kind of graphs by hand, we would draw a vertical asymptote like this with dashed lines, or this is showing dotted lines. Dash looks better, I think. Yeah, and I probably want it to be the same color as the graph. Okay. Anyway, that's just a visual indication that here's a point where the graph isn't defined, and not just that it's not defined. There's an infinity going on here. As you approach that x coordinate, your values go right through the roof. Actually, it's kind of fun that on the right-hand side they go vertically towards plus infinity, but just to the left of it, they go to minus infinity. This graph has what's called a huge discontinuity in it, a discontinuity that goes all the way from negative infinity to plus infinity, as far apart as two ends of a graph can get. Yeah, so that's a vertical asymptote. A lot of rational functions have such things in them, and they often represent physical quantities that have this sort of behavior. Like, you may have heard that it's impossible to go the speed of light. You can't get there. If you wanted to keep accelerating, getting closer and closer and closer to the speed of light, you'd have a graph like this that represented your energy. Actually, it would be the upside down of this. Here, let's put a minus sign on it. We can do it. You can have your energy starting at 0 and heading up towards infinity, and that's because your speed is getting closer and closer to the speed of light. But what that tells you in physical terms is the energy required to go to the speed of light is infinity, and so no physical object is ever going to get that much energy. And anyway, that's one example of many of places where in physics and even in economics and things like biology you'll see rational functions. Rational functions can appear in, for instance, the growth of a population. And if you have a vertical asymptote like this as the way a population is growing, that's really a problem, because it means that the population is going to infinity, and no ecosystem is going to bear an infinite amount of some quantity that's in its, or some life form that's in it. So yeah, that would be bad. So that's a vertical asymptote. It's possible to make yourself have vertical asymptotes, and here's a good trick. You use the factored form of the thing to create whatever vertical asymptotes you want. Like I have one here at 2. I can also put a factor in the bottom like x plus 1. And now I'm going to have a vertical asymptote also at -1. Let me zoom away a little bit and we'll see it. I'm going to add a line for that. X equal -1. I'll adjust it to look the same so that it's red and dashed. Yeah, so this is a pretty strange looking function right now, but it's surprising how often you want to create a function of this nature. There's another kind of thing that can go wrong with such a function, and I want to illustrate that for you by just changing one thing about this this fraction. I'm going to turn that plus into a minus. And do you see how my vertical asymptote just disappeared? Well, why did that happen? It's about the numerator now actually is something that factors. Before it was something that didn't factor. X squared plus 1 has plus and minus I as its zeros, but this guy factors as x plus 1 times x minus 1. Let's just look at that. Do the same, whoops, I wanted to do the same. Observe that we get the same graph, sorry I keep typing wrong, if we do the product of x plus 1 and x minus 1 up here. Look identical to what we had a minute ago. That's just showing you that the factorization works. Well, what's the domain of this? Because right now I would say we can cancel off the x plus 1s and get a much simpler looking expression, and that's true, but the domain computation is made before you do that cancellation. So x equals -1 is a problem spot on this graph. It's a place where it is not defined. Let's zoom in here a little bit. If you put your cursor on the graph and trace its value, and you come to the value where the vertical asymptote used to be, you see how it goes undefined at that moment? So, yeah, even though the vertical asymptote is no longer appearing, the graph isn't, the function isn't computable at that value. You have a place where it's not in the domain, despite the cancellation making things look better. Now, excuse me. Let's try getting rid of those x plus 1s in the top and the bottom. Looks like the same graph, doesn't it? The only difference is this thing is not quite the same graph because it's perfectly fine at -1. You know, it is defined there, so its domain only has +2 as a gap in it. Okay, so the sort of thing we just saw is called a hole, and it happens when there's a factor in the numerator that matches with a factor in the denominator. So yeah, you can find those. Let's talk a little bit about how you would go about finding such things. Transition to the book here, and there's a whole little section on how do you go about locating vertical asymptotes and holes in a graph. Well, there's a theorem on it. In fact, did I miss it? No, apparently I keep missing it. Okay. It must be beyond the spot that I was just looking at. There we go, theorem 4.1. That's what I had in my notes. Locating vertical asymptotes and holes. Let's just read this sucker. Suppose R is a rational function, which can be written as R of x is P of x over Q of x. And P and Q have no common zeros. Now that means that we don't have a hole. Then let C be a real number which is not in the domain of R. So if the bottom function q at c is not 0, then the graph has a hole. Yeah, I think they have stated this wrong, because where they've said they have no common zeros, well, you know what? It's actually at common zeros where you get holes. So I think that's actually a flaw in the book. I'm going to have to think that through a little bit. Well, anyway, if the bottom, p and q are the function, or the polynomials, right? So if the bottom at c is 0, then you got a vertical asymptote at c. So let me state it differently, because I do think the book has got a flaw right there. We'll write this down. Need to transition to this. All right, so what's the problem? You're going to have r of x is p of x over q of x. If the two of them have a common factor of x minus some number, so if x minus c is a factor of both, that's the situation where you get a hole. If, on the other hand, they don't share a common factor, and you've got something is really going wrong, if x minus c is a factor just of the q, but not of p, then you're going to get a vertical asymptote. And we'll just get lazy and abbreviate that VA for vertical asymptote. Basically, you look at the denominator, figure out where is it 0. That's places where you're either going to have vertical asymptotes or something else has gone wrong, in which case usually it's a hole. What else can happen? Well, there's a feature that these kinds of graphs often have. Might as well go back to our Desmos window and show you one. Yeah, actually, the graph we're looking at right now has this feature, which is if you zoom out a little ways, oops, wrong way, you'll notice that it's got this spiky looking thing where the vertical asymptote was, but as you get far away from the origin, far away from sort of where the interesting junk is happening, it just becomes a flat line. Now, look at the formula for that thing and try to say to yourself, why would that just be a flat line? It looks like it's the line, actually let's fill it in. It looks like it's just the line y is equal to minus 1. How did I type minus and not get a minus? Oh, I just was sloppy. All right, well that's a prime example of what's called a horizontal asymptote. The word asymptote just means another curve that this one approaches. And as we sort of work our way off to the right, you see how the red curve is getting closer and closer to the purple line. If we come back and look at the other side, the red curve again is approaching that purple line. So the line is an asymptote. Well, I want us to just look at the formula for this this particular rational function and see why it is that we would expect to just get a number when x was relatively large. So I usually like to say, well, what happens when x is 1,000,000? If x is 1,000,000, we got 1,000,000 minus 1 in the numerator, and we've got 1,000,000 minus 2 in the denominator. And, you know, 1,000,000 minus 1 is basically still 1,000,000. 1,000,000 minus 2 basically still the same size as a million. So that quotient is essentially a large number over the same large number, and then the minus sign out front makes it -1. That is something you can see pretty quickly if the polynomials involved just look like, well, they give you something that will be of approximately the same size. So yeah, let's move on to a new example. How about if we had x to the third minus 1 and x to the third minus 2? I don't know what kind of behavior that's going to have. Okay, let's get some funny business going on here around, who knows, some values in the near x equals 0. But when we get far away from where that asymptote is and where there's a little wiggle in the graph, what happens to the value of this thing? Oh, I really don't want that minus sign anymore. Take that minus sign off. There we go. Slightly different graph. It's just the other one flipped upside down. But do you see that it's got a horizontal asymptote? And how could that have been predicted? Well, when x is a big number, x cubed minus 1 and x cubed minus 2 are essentially the same. So we're dividing a number by itself there, and thus we get 1. If I wanted to get some other number, I might put a 3 in there, and then the horizontal asymptote is 3. Okay, so what does that say in terms of, how do we figure out what these horizontal asymptotes are? Basically, r of x will have a horizontal asymptote if p of x and q of x are the same size. And when you're talking about the size of polynomials, you mean what's their degree. And what that horizontal asymptote, and just trademark there, have the same degree. The actual value of that horizontal asymptote is, just look at the leading terms of the things and divide. Just rather the same thing that you do when you do long division. So it would be, well, I'm not sure if we need to write it out in general. I'd have to come up with names for all the coefficients of things, but better to just say it that way. Look at p of x and q of x, divide their leading terms. It's the ratio of their leading terms. Just as an example, we won't necessarily, well, I guess I'll try to draft this in Desmos too, but suppose we had 3x squared minus 2x plus 1 divided by 2x squared minus 11. Well, if we went and did that, I would just say, look, they're both degree 2 things. The leading terms are 3x squared and 2x squared. That means it's asymptotic to y is equal to 3 halves. Just as a check on myself, let's try to graph that thing. So what did I say for the numerator? I seem to be in denominator first, so let's put that one in. 2x squared minus 11. You see, while I'm typing, you get some pretty strange looking features when you have more or less random rational functions. The other one was 3x to the second minus 2x plus 1. Oh, I got a little funny business in there because I ended up with an x in the exponent. Type, what the heck? Minus? Okay. I think I was holding shift while I hit that. That's what it's supposed to look like. This is a graph that, well, you can see a couple of vertical asymptotes on it. I guess the bottom there must factor. But the thing we're really interested in is the horizontal asymptote. I said we were going to get 3/2 is the horizontal asymptote. So let's verify that. Sure enough, the black line looks like the line that the red graph is approaching. When we're zoomed in fairly close, actually, you know what? This thing goes towards its asymptote rather quickly, doesn't it? I guess that's because it's got squares in it. Well, on the other side, it's not quite as fast, but still, by the time we're out around 20 or so, it's hard to tell the red graph from the black line. Okay, so we've beaten asymptotes to death a little bit. There's a simpler question to ask, which is, what about zeros? What about the zeros of such a thing? This graph, I don't know if it has any zeros. Do you see any places where it hits the x-axis? It looks kind of close, but not in there. It's slightly below the axis there. And it's on the outer parts here, it's above the horizontal asymptote on both sides. So it doesn't seem like it's ever going to hit 0. So this is a graph that's never 0. Why could we have told that from the beginning? Let's just look at the numerator of it. Oh, can I do that? No, I can't. I wanted to select just the numerator, but I can't seem to do it. So p of x, that would be the thing that's in the numerator. It's 3x squared minus 2x plus 1. And let's turn the other thing off, and the other thing off. Yeah, it's a parabola. This is the sort of thing we might have done in the activity the other day, where you've got a parabola that's pushed up in the air above the x-axis. It never hits 0. And that actually is sad in a way, because what I would love to show you is how do you make a rational function actually have a 0? Yeah, it's pretty clear if you just know how fractions work. How do you get a fraction to be 0? The top has to be 0. So if you have a location where the numerator, the p of x polynomial, is 0, that's going to be a 0 on the rational function, with one exception. If the denominator is also 0 there, then you'll get one of these canceling effects, and again you'll have a hole. Okay, I've got a note here that I'm supposed to show you theorem 4.2. So let's transition over to the thing with the book. And then we'll look at 4.2. That's 4.1. Location of horizontal asymptotes. Yeah, okay, we got to read through this thing, but it's going to be what I just said. Suppose R is a rational function, it's px over qx, and then this is cool. It gives us the leading coefficients of p and q, a and b respectively. If the degree of p is the same as the degree of q, then you look at y equals a over b, that'll be the horizontal asymptote. That's the case we just looked at. Now, what about these other options? If the degree of p of x is less than the degree of q of x, what does that do? Maybe I should show you one of those on a Desmos. Hold on one sec. Transition to there. Pull up the Desmos. Suppose we had something in the numerator that wasn't such a big polynomial. It was just maybe a linear thing in the numerator. Got to turn that back on. Turn this one off. That thing is going to go to 0. For sure. And let me think about what it happens at 1,000,000 to you. 2x plus 1 when you're at 1,000,000 is 2,000,001, right? But what is 2x squared minus 11? Well, 1,000,000 squared has 12 zeros in it. It's a trillion. So, is that right? 12? Yep, 12 is a trillion. This is a much bigger number in the bottom than that thing in the top is. The power makes it bigger. So when we go to large values of x, the numerator is a puny little thing compared to the denominator. And that means if you get a small number on top of a very big number, you're heading towards 0. Well then, what about the last case of this theorem in the book? Here we've got the degree of p of x is greater than the degree of q of x. The numerator has a higher degree than the denominator. Let's see if we can make Desmos do a graph that looks like that. Here, I'll just change this to an x cubed in the numerator, so we've got a higher degree in the numerator. Is this thing going to have a horizontal asymptote? No. Is it going to have a zero asymptote? No. What it's got is weirder, and later we'll call a thing like that a slant asymptote. Well, actually, really soon we're going to call that sort of thing a slant asymptote. But it's certainly not a horizontal one, and there actually is a straight line that this graph seems to be approaching. That's just not a horizontal one. All right. So in my notes it says to look through example 4.1.4. So I gotta get back to the book to do that. And 4.1.4 is just on the next page. So the first one of these, 5x divided by x squared plus 1, the thing in the numerator is only degree 1, the thing in the denominator is degree 2. So when x is 1,000,000, we've got 1,000,000,001 down below, and we've only got 5,000,000 up above. 5,000,000 seems like a big numerator, but not when it's compared to a trillion. So yeah, that'll go to 0. This is the case where the degree of the numerator is smaller. You get a horizontal asymptote at 0. Here, in number 2, we've got x squared minus 4 in the top and x plus 1 in the bottom. Having that higher degree in the numerator says it's not going to go towards a horizontal asymptote at all. And this one is, at first glance, this is really bad, right? We've got a cubic in the numerator, but only degree 5 in the denominator. Sorry, degree 1, the wrong number 5. But they have written it funny. And so I guess this is just an object lesson that we should be careful to look at the order that things are written in. Here, the leading term of this polynomial is actually written on the end, and it is a degree 3 thing. So the ratio of the coefficients of those guys is 6 over minus 2 comes out to negative 3. So yeah, those guys have. This one has a horizontal asymptote at negative 3. The first one has a horizontal asymptote at 0. The middle guy doesn't have a horizontal asymptote at all. All right, one last thing to talk about is this other case where the asymptote, look at that one, it can be at a slant. A slanted asymptote. In fact, asymptotes can be things other than lines, which we'll see in a bit. But I think that one is too hard to do. Let's see if I do. No, I don't want to do this. I want to have a slant asymptote that's carefully cooked up so that we don't have to factor anything too crazy. Okay, so what I'm going to put in is x to the third minus x in the numerator, and x plus 1 in the denominator. Oops. That's so funny. I thought I had this worked out in advance. Gee, I was expecting to see a rational function when I put that in, and I'm not. When I put x in, it's a parabola looking thing. When I put x plus 1 in, it's a parabola looking thing. But watch what happens when I put in x plus 2. It stopped being a parabola looking thing. Now it's got a vertical asymptote. It's got a vertical asymptote there when x is negative 2. And then it does some other funky business. It looks like it is, it's a little hard to follow what that might be. So let's just quickly do a little long division and see why long division is the key to slant asymptotes. I don't understand why the book doesn't do this the way I'm about to do it, but whatever. So let me transition over to the doc cam. Okay. So the polynomial I had just now, the polynomials I just had, were x cubed minus x in the numerator. Oh. And then x plus 2 in the denominator, right? And let me just simplify that by doing long division. Now, I know that this is currently got a domain that doesn't include x is negative 2. Right? It'll have a vertical asymptote at negative 2, which we actually saw in the graph a second ago. But what about its other behavior? Try dividing x cubed. I'm going to do long division here, even though I could do synthetic division. We get a little space for the quadratic terms, minus x. And a little space for the constant terms. Divide that by x plus 2. X goes into x cubed, x squared times. Multiplying back, we get x cubed plus 2x squared. And then when we subtract, we'll get, well, negative 2x squared minus x. Keep going, though. How many times does x go into minus 2x squared? That goes in minus 2x times. Multiplying back, you get the minus 2x squared. That's good, so those will cancel. And then minus 4x. When we subtract that from what's above it, negative x minus negative 4x, I think that's 3x. Does x go into this? Why, yes it does. It goes in 3 times. And 3 times that gets us 3x plus 6. And when we subtract that, we end up with a remainder of minus 6. That's our remainder. Oh, I've gone right off the bottom of the page, haven't I? So, you follow the long division? But this means, let me come back to what our r of x is. R of x can be re-expressed as the quotient we got plus, well, I might as well say minus, because it's 6 is the remainder we got, divided by x plus 2. And this guy holds how our asymptotic behavior, it is literally the thing that will be asymptotic to. And this other piece is guaranteed to go to 0 as x gets bigger. Because why? That's a remainder. And even if we had some other polynomial in the bottom, this remainder thing might be itself a polynomial. That could happen. But it would be guaranteed to have a degree smaller than the one in there. That's the way remainders work. They're smaller than the divisor. Well, that means this part is something that's going to go to 0. So what I'm trying to get at is that in the long term, this rational thing is going to approach this polynomial thing. It's interesting behavior. Let's end today by just making a graph of that last thing, and we'll see that in fact the strange looking graph is pretty reasonable once you've done some long division and you find out what its asymptote is. So the other graph I want on here is x squared minus 2x plus 3. And a lot of it's sitting there. X squared minus 2x plus 3. Oops. Oh, keep going one step too far. There it is. Oh, I got to turn it on too. And maybe we should make its color different so that it does look a little different from the thing. There we go. Yeah, you see, the red graph had all kinds of craziness going on. It has some zeros where the numerator was 0. It's got a vertical asymptote where the bottom of it was 0. But if you get far enough away from all that funny business, if you let x get to sufficiently large values, it ends up just approaching this parabola, the blue parabola. See that? Now, that's an example that's a little exotic. More often, once you do the division, you're going to get a linear thing. And maybe we should. I said I was going to quit, but let's just do one last thing of these things that has a slant asymptote. Yeah, how about x to the second minus 1? That's for the numerator. And the denominator will just be x. That's an easy example. Do you see why it has a slant asymptote? Well, try dividing x into x squared minus 1, and you will get something that this graph is going to approach. You don't. Yeah, might as well do that division too, right? What will the division give us? X goes into that, x times. I better actually divide, huh? Oh, sorry, I forgot to do the transition, so I was not showing you the graph that I was just building. Let's try that again. Yeah, here's the graph I was looking at. I had put the polynomial x squared minus 1 in there, divided by x, and it's kind of strange looking, but it is a case where you've got a slant asymptote. Right. Last thing then, we're going to transition back to this DocCam, and we'll do that division. We have x squared minus 1. Let's better leave a little space for the things. Divided by x. X goes into x squared x times. Multiplying back, you get x squared. Just subtract, you get minus 1. So that's a remainder. And so this thing actually looks like x plus negative 1 over x. That means the slant asymptote there is the polynomial part of that. Let's transition back to the graph and draw our slant asymptote, which is just y equals x. Yeah. Indeed, the green line is a straight line, and the blue graph is getting closer and closer to it. All right, I think we'll call it there. That's everything you need for section 4.1 homework.